In this video, we're going to walk through how to create a simple web server in C that will be run on the Raspberry Pi Pico W. This web server can display things like a series of HTML pages, but can also contain interactive aspects like live analog to digital converter readings and the option to toggle the GPIO on the Pico W. We will achieve this using server-side includes or SSI and the Common Gateway Interface or CGI, but more on those in a bit. So the outcome of this tutorial will be a template web server that you can adapt to whatever your project needs are. We would highly recommend following this tutorial step by step so that you can learn how each bit works, but by all means clone the template from the GitHub repository and use the timestamps to jump to the portion of this video that explains the parts you need. In order to generate the web page that is hosted on the Pico W that we're currently showing on the screen now, we're going to use server-side includes to tell us the current reading of the analog to digital converter, the internal pin, that's the one which is also used as an internal temperature sensor, so we might as well display the current temperature. SSI will also be used to query the status of the onboard LED. The buttons will use the Common Gateway Interface or CGI to run a command to turn the LED on the board on or off. As you have come to this video, then you are obviously interested in learning, and whether that is to progress your career or simply for entertainment, this video's sponsor Brilliant.org makes learning fun and engaging with thousands of interactive lessons on topics such as maths and computer science. Brilliant's lessons help you learn by doing. Interactive elements like drag and drop simulations really let you engage with concepts so that you actually understand them. I personally really enjoyed Brilliant's brand new course called How Technology Works, where I learned how technology that I use every day, such as wireless communication and GPS systems, actually work. Go ahead and try everything Brilliant has to offer, free for 30 days, by visiting brilliant.org/learn-embedded-systems, or click the link down in the video description. The first 200 of you to sign up with that link below will get 20% off Brilliant's annual premium subscription. Now let's move on to what you'll need for this tutorial. We will obviously need a Raspberry Pi Pico W, and we will use the Windows VS Code toolchain that we previously demonstrated in the video in the cards above. This tutorial is not Windows exclusive though. We will also be using a couple of Python scripts, so make sure you have Python installed. We will need at least version 1.5 of the Pico SDK, so if you're using an older version, then just make sure you pull the updated version. We will use the LWIP TCP IP library, which is included in the Pico SDK. And this is a library that is designed for use on embedded systems, and there is a wiki that I will link down below which explains most of the functions of this tool. Before we start programming, we're going to take a look at some of the basic concepts that we will use. To remind ourselves of the project outline, we're going to create a web server, also called a HTTP server, which will display a series of HTML pages to a user, and this web server will be hosted on the Pico W. We want to display some current values of analog to digital converter voltage, temperature, and GPIO status on a web page, and so we intend to use SSI or server-side includes. This is a method of telling the server to include some extra information in a web page. In a HTML document, we include a tag with a directive and maybe some parameters. This tag looks a lot like a HTML comment, which it sort of is. This is so that if the directive isn't enabled on the server, then the end user won't see it. When the user requests the HTML page with a tag calling, say, the voltage directive, the server sees the SSI tag, and in turn triggers an SSI handler function, which runs some code, and the result of this function is embedded into the web page. When we want to use the buttons to turn on and off the onboard LED, we do this by using the CGI or the Common Gateway Interface. And this essentially enables the web server to run an external program or function. When the user visits our web page and presses the LED on button, a HTTP request is sent to the server. This request will come in the form of something like this, where the LED.CGI part of the request triggers the CGI handler, which is responsible for turning the LEDs on or off, and this handler is passed the parameter, say LED, equal to a value of 1. The handler checks that the parameter is for it, and then checks the value and whether that corresponds to turning on or off the LED. The difference between when you should use SSI or CGI boils down to what you want to do on your web page. An SSI function is run every time a web page with an SSI tag is loaded, whereas a CGI function is only run when a specific request is received. Right, with that explained, let's get on with creating our project. Firstly, we're going to clone our basic RP2040 VS Code template into a new folder using the command git clone and then the following link. This is just an empty project, but with all the configuration files that we need. We can then open this folder in VS Code and select the Pico ARM GCC kit when prompted. This should then configure our project. We can rename the header.h file to SSI.h and then create another header file called CGI.h. We need a couple of external files. These will be easier to copy from our final GitHub repository. And we need the LWIP opts header file, which can be found in the Pico SDK if you go digging, but we've changed a couple of options, so I'm just going to copy it across from our repository. We need a makefsdata Python script, which is a Python version of a C function that is actually included in the LWIP library, but I had numerous problems with the C function, so I just found this script online. This Python script converts HTML and their associated files into a C file that can be included in our program that we then upload to the Pico W. We finally need to create a folder called HTML files, and this is where the files for our web server will be stored. Next, we need to edit our CMakeLists file. This CMakeLists file is a little more involved than some of the other CMake files that we've done before, but it follows the same points. After the minimum required CMake version, we declare a variable called program name and set it to, you guessed it, the name of our program. We create another variable to set the Pico board to the Pico W. We then name the project and initialize the Pico SDK. Next, we need to run the Python script we downloaded. I used the message function just to alert the user what's happening at this point as a bit of a debug message, but you can ignore this if you want. We can use the CMake execute process function with the command argument and then the command that we want to run. In this case, we want to run the Python script, so we use py makefsdata.py. We need to include the working directory to ensure that CMake finds the script. Add the Main.c file. I just replaced the template name with our program name variable. Then we include the current working directory to ensure that all the header files are properly detected, and then we link the Pico CYW43 arch LWIP thread-safe background function, bit of a mouthful that one, as well as the Pico LWIP HTTP, Pico stdlib, and the hardware ADC libraries. Then we enable USB STDIO for debugging messages and disable it over UART. Then we add some extra outputs to ensure that the UF2 file is generated. Now, let's get on with writing our main.c file. Firstly, let's start with the header files. We include the LWIP HTTPD file, which contains all the web server functions. We also need the Pico standard library and the CYW43 header file as well. We also want the LWIP opts.h file, CGI.h and SSI.h header files. We then declare two global variables that will contain your Wi-Fi SSID and password. Then, in our main function, we firstly call stdio init, which enables all the things we need like USB communication, and then we initialize the Wi-Fi chip using the CYW43 arch init. Then we enable Wi-Fi station mode with the CYW43 arch enable STA mode function. And to attempt to connect to our Wi-Fi network, we put the CYW43 arch Wi-Fi connect timeout millisecond function with the arguments of the Wi-Fi SSID and password, and telling the function we're using WPA2 encryption, and a timeout in milliseconds. In the loop, we put a debug message, which is just telling the user that we are trying to connect. And outside of the loop, which should run when we have connected, we just print a message telling the user that the connection has been successful. Then we initialize the HTTP server with the LWIP function, httpd init. We also call two functions, SSI.h and CGI.h, that we will write later. Then, to finish off the main function, we simply enter an infinite while loop. Now, moving on to our SSI header file, we're going to start with the includes, as always, and we include the HTTPD file and the Pico hardware ADC, as we're obviously going to be using the analog to digital converter. We also need the Pico CYW43 header. Then we define a character array of the SSI tags that we want to be able to use. We use the volt tag for the raw ADC voltage, then the temp for the corrected temperature reading, and LED for telling us whether the LED is on or off. You can obviously adapt these to how you want in your programs, but make sure that you keep the length of these tags to below 8 bytes, because that's the default maximum length. Now we create our SSI handler, which takes the arguments of the tag index, i.e. if temperature is selected, then that's the second in the tag array, so a value of 1 will be passed to the function. A pointer to a character array called PCInsert, which is a buffer that will store the information we want to display, and then an integer which tells the function how big that buffer is. Inside this function, we define a variable called printed, which will be used to check how many values have been stored in the buffer. Then we create a switch statement, which checks which index has been passed to the SSI handler, to see which tag has been requested. Case 0 was the volt tag, and so we simply read the analog to digital converter voltage using the ADC read function. We then apply the correct conversion factor, and then we store this value in the PCInsert buffer using the snprintf function. Case 1 was the temperature tag, so we do the same process of reading the analog to digital converter, but instead we convert it to the temperature in Celsius. Then we store the result in the buffer. We go over how to use the onboard temperature sensor in the video linked in the cards above. Case number 2 was the LED status and checking whether it was on or off. We can check this using the CYW43 Arch GPIO get function to check if the LED is on or off. This function returns a boolean with 1 being the LED is turned on. We then simply use an if-else statement to store either the words on or off in the buffer. Finally, the default case simply returns a value of 0 for the printed variable, which indicates that nothing was stored in the buffer. We then simply return the printed variable. To initialize the SSI handler, we create a short function called SSI.init, which simply initializes the analog to digital converter, enables the temperature sensor, and selects the correct analog to digital converter input. We then use the HTTP set SSI handler function so that the program knows what function to run when the SSI request occurs. This function takes the name of the handler function as well as the size of the tag array. Now, let's move on to our CGI header file. We include the HTTPD header file and the CYW43 Arch file. Then we create a function called CGI LED handler, which will run every time a request to turn on the LED or to turn it off is issued. This function takes the arguments of an index, the number of parameters in the request, an array of those parameters, and the associated values. In this function, we create an if statement to check that an LED function has been called and ignore everything else. And we use the strcmp or string compare function for this. We only check the first element in the parameter array because we don't care if there are any more parameters. We then create an if-else statement to check if the corresponding value of that parameter is a 1 or a 0, and then we turn the LED on or off accordingly with the CYW43 GPIO puts function. After this if statement, we simply return the index page, which we haven't written yet, but it will be /index.shtml, and so this is so that the user sees the main page once they've pressed the button. If you don't return a value here, once the user has pressed a button, they're likely to get an error saying server return no data or something along those lines. Next up in this file, we create a tCGI struct called CGI handlers, which contains a list of the CGI handlers, or the CGI requests and their corresponding handler. We only have one in this program, so we say that for any request for /led.cgi, this will trigger the function we just created, but you can add more to this and have different requests based on different functions you want to create. Finally, we create an initialization function called CGI.init, which calls HTTP set CGI handlers with the struct that we just created, and then the number of handlers, in this case just one. And now we're finished with the CGI header file. Now I think we're ready to move on to the web pages that we are going to display. We just want a simple setup of only one main index page, and we're going to use the file format shtml. S in front of HTML tells the server that there is some SSI or server-side include content within the page. You can have a series of web pages in the HTML files folder, and you aren't just limited to one. So let's create index.shtml and use the standard HTML page with a title in the head tags, and then in the body we're just going to print a heading and to write the bits where we want to display SSI tags. SSI tags are included using this format, and I'm going to repeat this for each SSI tag that we previously created. Then we can move on to the CGI requests, for which we are going to create two buttons that will send /led.cgi HTML request with a parameter called LED with a value of 1 to turn the LED on and a value of 0 to turn the LED off. And now that's our web page finished, nice and simple. I think it's relevant that I quickly cover the changes we made to the LWIP options or LWIP opts.h header file. And at the bottom of this file, we defined a few values which enable the web server, SSI, and CGI. We then include our converted HTML-C file called htmldata.c. Now we can get on with building our project. After any changes to the files in the HTML files directory, you must reconfigure the project. You can do this by going to the CMake extension and then clicking the reconfigure button. This is because the makefs Python script is only called when CMake configures the project. Once configured, build the project. Hopefully it compiles without error. We then upload the generated UF2 file to the Pico by pressing and holding the boot select button whilst plugging it in, and then clicking and dragging the UF2 file from the build folder into the mass storage device that has just been created. The Pico W should then restart and connect to the Wi-Fi network. If you open a serial monitor and point it to the COM port that the Pico is attached to, then you should see some debug messages saying the server, SSI and CGI handlers have been initialized. If you visit the IP address of the Pico W in your browser, to find this you might have to log in to your Wi-Fi router to get this, but once you have it and you navigate to it, you should see your web page loaded up with the values for the ADC voltage and temperature displayed, as well as whether the LED is on or off. To update these values, simply refresh the web page. If you have a go at pressing the buttons, then you should see the onboard LED on the Pico W turn on and off. So that's everything for this video, and we have covered how to make a basic web server with LWIP and how to make it more interactive with server-side includes and the common gateway interface. Hopefully this video, alongside the project template on GitHub, linked down below, will provide you with everything you need to adapt this and use this web server in your own projects. Please let us know how you end up using them down in the comments. If this video has helped you, then please leave a like